Hi everyone, I'm Arun. I'm a high school student and I've been doing competitive programming for about 3 or 4 years. I hope I'm clearly visible and audible to everyone. Uh, I request if you can type yes in the chat so I can confirm. Am I audible and visible? Okay, great. Thank you. So today we're going to take up combinatorics and I hope my screen is visible now. So we're going to take up combinatorics today, and combinatorics is not an algorithm or a data structure, and yet we're discussing it in DSA. Why is that? It's because combinatorics is a part of mathematics that will help us solve problems of a very specific type, which is something we often come across. So, what kind of problems can we solve using combinatorics? Combinatorics will fundamentally help us solve problems which involve counting. And maybe we have to count the number of ways to do something or the cardinality of a set, if you're familiar with set theory, right? So for today's session, I'll try to keep it more or less theoretical and more mathematical in some sense. And we're going to cover the computational aspects in part 2, right? So we're going to begin with counting principles. And this will really be a way to count things in a smarter way. But before we get to that, I'd like to discuss two things which will seem to be irrelevant, but they still make sense in a while. So, so there's something called, so I'm going to begin with types of events, right? And this is not going to be an exhaustive list, but I just need you to be aware of two types of events. The first one is independent events. And the second one is mutually exclusive events. So with these two types of events, what exactly are independent events? I say that events A and let A and B be two events, right? If the occurrence or non-occurrence of A doesn't affect the occurrence or non-occurrence of B, then we call these two events independent. Right. So if I have two events, A and B, and if the occurrence of A does not affect the occurrence or non-occurrence of B, and the occurrence or non-occurrence of B does not affect the occurrence or non-occurrence of A, then we call these two events independent. And if that sounds like a mouthful, then I'll just say that if if uh, if whether A happens or not does not affect whether B happens or not, we call them independent. Sticking to mathematical examples, rolling a die and tossing a coin are independent events, because whether or not I get a heads on a coin and or a tail on a coin does not affect what number I'll get on the die. So this is what I mean when I say independent. And I'll really appreciate if you could type in some examples of independent events and we can discuss those, right? Perhaps you can do that on the chat. Yes, exactly. Winning a toss and winning a match. I love that example. So whether or not you win the toss has nothing to do with whether or not you win a match, and therefore these two events are independent. And therefore, uh, the number of ways in which I can win a toss and win a match will be the number of ways in which I can win a match times the number of ways in which I can win a toss. And I'll come to that in a while. But yeah, we'll discuss that. Right. So now that we know what independent events are, I want you to be aware of mutually exclusive events. And mutually exclusive events, or they're also called disjoint events. And here's how I'll define them. Events A and B are said to be disjoint if the occurrence of A guarantees the non-occurrence of B, and the occurrence of B guarantees the non-occurrence of A. What that means is, if event A happens, then I can be sure of the fact that event B will not happen. And if event B happens, then I can be very sure of the fact that event A will not happen. Or another way to state that is that event A and event B cannot happen at the same time, right? And when I say time, I do not mean at the same instant, but I mean if event A happens, then I can be sure that event B will not happen, right? So so one example of this can be that, let's say you're in for some sports tournament. Again, one of you give me a sports example. Then let's say you're in for a team selection, and either you will be selected in the team or you will not be selected in the team, and these two events are disjoint, right? If I am selected in the team, so if I am a part of the team, then it is guaranteed that I will not be a part of the team, right? I hope that not part was clear for everyone, right? So that's one thing. Another way to say that is that if I have a set and I can partition it into two disjoint subsets. That is to say, if I have a set A and I partition it into two sets B and C, such that those two sets are disjoint and A union B and B union C equals A, then we can see that then they can basically represent those events, right? We're going to see many examples where sets can be used to represent events. Anyway, so I have already written down these things before, so you can quickly have a look, right? And if you'd like to share some examples of all right, yes. So yeah. So if tennis match happens, then it is guaranteed that it's not raining. Yes, that is correct. So if it's raining, it's guaranteed that a tennis match will not happen. And if it's if a tennis match is not happening, it is guaranteed that it. All right, now I see a problem there, but yes, that's a very reasonable argument, assuming that whenever it's not raining, a tennis match will be happening, which might not necessarily be true, but we can definitely stick to that, right? Also, exhaustive events, right? So let me take an event and I'll partition them into two subsets. Then if all the possibilities from A and B cover up all the possibilities which were in my original event which I partitioned, then those two sub events will be exhaustive, right? All right. So now we come to our counting principles, and these will help us really rethink how we fundamentally count. So we have two principles, and I'll first like to talk about the multiplication rule. It says that if an event A can occur in m ways and another event B can occur in n ways, such that these two events are independent, then the number of ways in which they can occur will just be the product of the number of ways in which both the events can occur. What that means is, if I were to flip a coin and roll a die, then when I flip a coin, I have two possible outcomes: a head or a tail, right? Let me try to make that. I can either get a heads or I can get a tails, right, on a coin. And on a die, I can get either 1 or 2 or 3 or 4 or 5, right? I think it's like this. This event and this event, the outcomes of these two events are independent. And therefore, the number of outcomes I'll have when I both flip a coin and roll a die will be 2 times 6. So one way to look at that can be to just enumerate all possibilities. Give me a second, I will remove this. All right. So let's say you decide to flip the coin first, and that will have 2 outcomes, a head or a tail, right? And then I can decide, okay, fine. Now I'll roll the die, and I can get 6 possibilities. Oops. Corresponding to 1, 2, 3, 4, 5, and 6. Right? And similarly, we have 6 possibilities here. And if you see this particular possibility corresponds to getting a head on the coin and a 1 on the dice, and this will correspond to getting a head on the coin and a 2 on the dice, and so on, right? So we'll have 6 plus 6, and that'll be 12 possibilities, or you could say 6 times 2, right? And this is why the fundamental principle of counting's the multiplication rule fundamentally works. Okay, apparently the audio isn't clear. Is that true for everyone, or I'm hoping I'm clear, right? Yeah, perfect. Thank you. All right. So now we come to the addition rule, and this is again saying that if I have an event which can be split into 2 disjoint events, disjoint and actually exhaustive events, where one of them can happen in m ways and the other can happen in n ways, then the event can overall happen in m plus n ways. So it's like saying that if I knew the number of ways in which a team could be formed such that I would be selected, and I knew the number of ways in which the team could be formed such that I was not selected, then if I add both of them, then I get the number of ways in which the team can be formed in total, right? Because if I am selected, it is guaranteed that I'm not selected, and if I'm not selected, it is guaranteed that I am not selected, right? So that is the basic idea behind the addition rule. And another way to think of it is that let's say you had a class and you had to count the number of people, the total strength of the class, that is to say. Then one way to do that is to count the number of people who are present in the class, and then count the number of people who are absent in the class. And then if you add both of them, you will get the total strength of the class, right? And these two sets are disjoint. These two sets are disjoint because if you're present, it means you're not absent, and if you're absent, it means you're not present. And therefore, these are disjoint sets. All right. Now let me just quickly demonstrate this principle from set theory, right? This is true because if I were to have a set X, and this were to be equal to 2 sets, to a union of 2 sets A and B, such that their intersection was the empty set, which means these 2 sets are disjoint. This just means that these 2 sets are disjoint. Then the cardinality of X will be the cardinality of A plus the cardinality of B. A way to look at this is that let me call this box as X. Then if I partition it in such a way that everything that's to the left of this partition is not to the right of this partition, and so on, then if this is A and this is B, this in total is X. Then I'm saying that the number of elements in X is the number of elements in A plus the number of elements in B. Okay, so apparently the audio is low. and it's going up and down. Okay, that's interesting. I hope everything's fine from my side. At least I checked it once. So yeah. Anyway, now that we know these two counting principles, we can quickly get to some further concepts. And what do we have next? A quick review of factorials, right? So what is a factorial? I hope you are already familiar with this. If you're not, I'll just give you a quick introduction, right? So if I were to say n factorial.
Hi, Aryan. There's a doubt
Yeah,
in the chat. Please check.
Let me just, yeah. Yeah, what is xi enclosed in bars means? So is this what you're asking? This thing? Yes, cardinality means the number of elements here, the number of elements in the set, right? Another way to denote that is n of a. This is the same, right? Yeah. Great. So coming back to factorials, so we define factorial in the following way: n factorial is 1 times 2 times 3 and so on, all the way up to n. This means n factorial fundamentally means I'll take all the positive integers from 1 till n and I'll multiply them, and that is denoted by n factorial, and this exclamation mark just means that I'll multiply all the numbers from 1 to n and that will be my answer, right? Also 0 factorial is conventionally taken to be 1. Also if you this is a common recurrence with factorials. It says n factorial is n times n minus 1 factorial. And what this means is that if I take all the natural numbers from 1 to n and I multiply them, that's the same as taking all the natural numbers from 1 to n minus 1, multiplying them, and then multiplying n to it. So if you can imagine this is just n minus 1 times n minus 2 and so on till 1. And this is if you just multiply n to it, then you get 1 times 2 times 3 times 4 and so on till n. I hope that's clear, right? So why do we need to talk about factorials all of a sudden? Right? It's because a factorial fundamentally solves one problem, and that problem is arranging n things in a line. So let's say I had n things, right? Let's say a1, a2, a3, and so on till an, and I had to arrange all these things in a line. The answer comes out to be n factorial, and let me just quickly explain how. For simplicity, let me take 3 objects, right? A, B, and C. And I need to find the number of ways in which I can arrange A, B, and C in a line. So if I were to just enumerate them, it'll be A, B, C, B, A, C, B, A, A, C, and we'll have C, A, B, and C, A, right? All right, I should increase the sensitivity of my microphone. Let me just check that really quickly. So, all right. Hello, is this better? I hope it is, right? Thank you. So yeah, these are the number of ways in which I can arrange A, B, and C in a line. But instead of enumerating, how else would I got the same answer? And that is to say, let us consider 3 blank spaces, right? And I have 3 objects. I don't really remember my rating. You can check out my username. It's Aryan_02, right? So it's so yeah. What I was saying was it's A, B, and C, and we have to arrange these in a line, then for the first blank, I have three choices. I can choose any one of these, right? And that gives me three choices. And whatever I put in the second blank is independent of what I put in the first blank, because actually it's not that independent, but in the sense that the number of ways in which I can put anything in the first blank is independent of the number of ways in which I can put anything in the second blank, right? So I have two choices in the second blank, and I multiply because these are independent events. And I'm left with just one choice here, so I multiply this by 1, and I get 6 as my answer, right? For the case of 3, we're getting 3 times 2 times 1. If these were n events, that would be n times n minus 1 times n minus 2, and so on till 1, and that would have been n factorial. And if you can see here, 6 is nothing but 3 factorial. There's 1 times 2 times 3, right? All right. So we're done with factorials, and now we'll come to permutations. Yes. So permutations are the very same idea of arrangement of things in a line, but this time we'll not arrange everything in the line. What we'll say is I have n objects, right? And from these n objects, I'll pick any r objects, and then I'll arrange them in a line, right? So total 9 combinations can be made. How exactly? I'm a little unsure of that, so I'll see if I can get to that in a while. So moving on to permutations. So I have n objects, and I need to pick r objects out of them and arrange them in a line. So what I'll do for this is that I'll say, okay, fine, I have r blanks, right? And let's say this is these are r blanks, and I need to pick n objects. So for this, I'll have n choices, right? For this blank, I'll have n minus 1 choices. And for this blank, I'll have n minus 2 choices, right? And so on. For this blank, I'll have n minus 3 choices. And so on. For the last blank, I'll have n minus r plus 1 choices. Why is that? It's because I have r blanks. So I don't have n blanks, but I have r blanks. Yes, exactly. It's n minus r plus 1. So this thing is my answer, but I'd like to represent this in terms of factorials. Okay, how plus 1? I'll explain this. So for the first blank, it's n. For the second blank, it's n minus 1. For the third blank, it's n minus 2, right? So for blank 1, it's so whatever we're subtracting is 1 less than what blank it is, 1 more than what blank it is, right? In fact, 1 less. So this is n minus 0, n minus 1, n minus 2, n minus 3. So n minus r plus 1, right? If you just try it with a few examples, you get an idea of this. I really encourage you to do that. Right? All right. So now that we're done with this, we have to represent this in terms of factorials because we like factorials. Because factorials are just a compact notation to write things, right? So what can we do to turn this into factorial? Let me call this 8 as my answer, right? And what I see here is that it's n times n minus 1 times n minus 2. I'm multiplying consecutive positive integers, just like factorial. But I'm stopping here at this point, n minus r plus 1. So what if I do this, right? I take this a, and I'll multiply and I'll try to complete the series, right? So after n minus r plus 1, my next term will be n minus r, and then there will be n minus r minus 1, and then n minus r minus 2, right? And it will go on till 3, then 2, then 1. Yes, I'm doing exactly that. I'm multiplying both sides by n minus r factorial, because now that you look back at this, it's n minus r factorial, because this is 1 times 2 times 3 and so on till n minus r. So this is just a times n minus r factorial. And if you look at this thing multiplied by this thing, right? This is nothing but n factorial. N times n minus 1 plus times n minus 2 and so on, times 3 times 2 times 1. That's just n factorial, right? And therefore now I divide both sides by n minus r factorial, and we get our answer in terms of factorials, right? N minus r factorial over n factorial. Sorry. In fact, it's n factorial over n minus r factorial. Now, why did we choose to do this? It's just better compact notation. I mean, I wouldn't like to write a whole product in just to explain someone my answer, right? So this compact notation will help us. Now I'll move on to some more compact notation. That was n factorial over n minus r factorial. And we denote this as NPR. A permutation of n things taken r at a time. Right? So I hope that's clear. And now I'll talk about what's called the principle of bijection, because we require it to derive our result of combinations. So one of the most elegant things you'll ever see in combinatorics will be when you try to find two different ways to count the same thing. I'll write that down. Find two different ways to count the same thing. And we're going to use this principle time and again to solve even the most difficult problems in combinatorics. And these ideas will be very useful when we're trying to prove things. So for now, what this means is that if I have two sets, right? Let's say I have a set A and a set B, and I need to count, and I need to find the cardinality of set A. If I'm able to find a mapping of all elements from set A to a unique element in set B, such that that is to say a bijective mapping, right? In the sense that if I can map every element of A to exactly one element in B, then I can conclude that the cardinality of A is the cardinality of B. How? Imagine you have two classrooms, right? Now I need to calculate this. Now I need to count the strength of one class. A cardinality of a set is just the number of elements in that set. So if I have this set, right? Let's say I have set X equal to 1, 2, and 3. Then this is called the cardinality of X, and it just means the number of elements in that set. Right, exactly. Size of the set is cardinality. All right. So I need to find two different ways to count the same thing. And let's say I have a set A and a set B, and I find a bijective mapping from A to B. Then I can say that the cardinality of A is equal to the cardinality of B. One way to think about it is that if I have two classrooms, like two classes of students, right? Class 1 and class 2. And I need to count the number of people in class 1. I noticed that the number of people, I look at the attendance register of class 1 and I look at the attendance register of class 2, and I noticed that the last entry in them have the same roll number. And this should immediately mean that they have the same cardinality. But how will we prove it mathematically? And we do that by saying that, okay, fine. Two students are from class 1 and class 2 are related if they have the same roll number. So what I'm saying is that let's say roll number 1 from class 1 maps to roll number 1 of class 2. Roll number 2 of class 1 maps to roll number 2 of class 2, right? And if this is true for all roll numbers of class 1 and class 2, and every roll number of class 1 has exactly one roll number in class 2, and that is true the other way also, that every roll number in class 2 has exactly one matching roll number in class 1, then they'll have the same cardinality. That is to say, they'll have the same number of students, right? So just keep this at the back of your mind that we're going to use this principle in a short while. And now let's come to combinations. And combinations are fundamentally a way to select n things from R things. Over here, when we did NPR, right? We were selecting n things from R things, and then we were arranging them in a line. So okay, you're saying cardinality is an aspect of an ordered set. It's not necessary for the set to be ordered in order for cardinality to exist. We can have multi-sets that have cardinalities and all of that stuff. But yes, we can say that in some cases. All right. So I was going to talk about n choose R. That is to say, the number of ways to choose R things from n things. And what we said here was that this is arranging R things from n things in a line. How can I find the number of ways to choose R things if I know this already? One way to look at that is say I have A, B, C, and D, and E, and these are objects, right? I need to select any two objects from here. One way to do that is to say, okay, fine, I'll take I'll take two objects from here and I'll arrange all of them in a line. And for every arrangement of two objects in a line, I'll have exactly one selection corresponding to them. What does that mean? Let's say I select A and B, and I select B and A, right? These are two possibilities of arrangements. This is what NPR is actually counting, right? But these two have to be counted as the same when I'm counting them in combinations. That is to say, the number of selections. And again, if I select B and C, and I select C and D, they will be counted as the same. So these two will be two distinct selections of two objects from these 5 objects. Right. And if we had to take a simple example, let's say these were 3 objects, then these would be the total number of selections, right? And you would have A and C, and you would have C and A. These would be the total number of permutations of 2 objects from 3 objects, right? But now, if you look, these two are the same. These two correspond to the same selection. These two correspond to the same selection, and these two correspond to the same selection. So this is ultimately what we're saying is we'll have to divide by 2 to get the number of selections. I hope you'll all agree, right? Yes, you're right. NPR is counting extra A, B, and BA, and therefore we define n choose R. So what we say here is that n choose R equals NPR over R factorial. Yes, exactly. So what this ultimately gives us is that if I were to arrange those things, if these things were to be arranged, then for each R factorial arrangements, I have exactly one selection, and therefore we divide by R factorial. Okay, so now that we have reached this result, let us try to just formulate this in a better manner, and we'll call this n factorial over R factorial times n minus R factorial. I just took this and I divided that by r factorial, because again NPR this thing over r factorial. I hope that's clear. Okay, so this is how we invoke the principle of bijection, and now I'll invoke it again. How? There's a very famous identity with n choose r, and it's called Pascal's identity, and it says this: n choose r equals n minus 1 choose r minus 1 plus n minus 1 choose r. And I know it looks horrible right now. Like, who on earth could even think of this identity? It might seem like that. But one way to prove this identity can be to expand these, right? You can put this, you can use this formula n factorial over r factorial n minus r factorial. But we're not going to do that. Instead, we're going to invoke the principle of bijection, and that'll make all the calculations simplified for us. How? This thing, the left hand side says n choose r. What even is n choose r? It is the number of ways to choose r things from n things, right? So if I selected r things from n things, or you could think about it as forming a team of r people from n people, and this would be the number of possible teams. So I have r spots, and I have n people, right? Person 1, person 2, person 3, and so on till person n. I'll just bring it in higher. So person 1, person 2, person 3, person 4, and so on till person n, and we have to make a team of r people from here. Now I say, okay, fine. We'll look at person 1. Person 1 is either a part of our team or he is not a part of our team, right? These two events are disjoint. So in how many ways can I form the team of r people from n people such that person 1 is not included? The problem reduces to looking at these n minus 1 people, right? And choosing r people from here, because the team still has to be formed out of r people, right? And this is what this term corresponds to. N minus 1 choose r. Right? And if I were to look at this term, if P1, if I had to include P1, then I'm left with n minus 1 people to select from, and I have to select r minus 1 people because one spot has already been filled, right? So if if one spot is already filled, then I'm left with r minus 1 people to select, and therefore this term comes up. If you're familiar with Pascal's triangle, that looks something like this. It's okay if you're not familiar with it. All it's saying is that if you add this and if you add this, you get this. And this is why this is very popular, right? Also, I won't talk about that in detail right now. I'll cover that up in the next section. But just as a hint, this thing will be used as a recurrence relation to compute n choose r if we need to, right? All right. So we're done with that as well. And now we have just problem solving. So I discussed one problem, and this is going to be a pretty interesting problem. Consider these numbers: 0, 1, 2, 3, 4, and 5. I need to form a 5-digit number using these 6 digits, using any 5 out of these 6 digits, such that the number is divisible by 3. All right. So I'd like you to give it a while to make sure you understand the problem. How many such numbers can be formed from these digits such that my resulting number is divisible by 3. I hope you have at least have had an idea of what exactly we're going to do here. Now, what does it even mean for a number to be divisible by 3? I mean, what's the divisibility rule that will tell us? Yes, we have to find 5-digit numbers out of these divisible by 3. So, how can we form a 5-digit number out of these divisible by 3? Yes, sum of digits is a multiple of 3. So let me try to add these digits, right? I have 0 plus 1 plus 2 plus 3 plus 4 plus 5. That is just 15, right? This is the sum of these digits will be 15. 1 plus 2 plus 3 plus 4 plus 5. And 15 is divisible by 3. Yes, when we form numbers, 0 should not be at the first place because then it wouldn't be a 5-digit number, right? All right. So now that we have the fact that the sum of these digits is already divisible by 3, how can I form numbers which will be divisible by 3 because I'll have to remove one digit out of these in order to get 5 digits to form a number out of. So since the sum is already divisible by 15, I'll have the only type of numbers that I can remove from these digits have to be divisible by 3. Because if I remove a number which is not divisible by 3, then my sum will no longer remain divisible by 3. So for example, if I remove 3 or if I remove 0, my sum will still remain divisible by 3. If I remove 0, the sum remains 15 because 1 plus 2 plus 3 plus 4 plus 5. And if I remove 3, then my sum is 1 plus 3 plus 4 plus 5, which is 1 plus 2 plus 4 plus 5, and that is 12. And 12 again is divisible by 3. So I'll make two cases. Case 1. If I omit 0, in that case, I need to make a 5-digit number out of these. So 1, 2, 3, 4, 5. I have 5 blanks, right? And what I'll do here is I have 1, 2, 3, 4, and 5 as my digits. And I'm going to arrange these in a line because every arrangement of these digits in a line will correspond to one unique number. And therefore, I have 4 things to arrange and 5 things to arrange and 5 blanks. So my answer will be 5 factorial for case 1, right? Yes, the answer of 5 factorial times plus 4 times 4 factorial is correct. And I'm getting to case 2. So if in case 2, I'm going to omit 0 I'm going to omit 3 as I said before, right? And I again have 1, 2, 3, 4, and 5 spaces. And this time the numbers I'm considering are 0, 1, 2, and I'm going to omit 3, then 4, and 5. Now I need to arrange these numbers in a line, but notice that 0 cannot be over here because if I fill 0 in the first blank, then my number will no longer remain a 5-digit number, right? Therefore, I'm going to say that I have only 4 choices here. And for this blank, I can put 0 here and I used 1. So I'll still have 4 choices. And then times 3, times 2, times 1. I hope it's clear why I did that, right? So this is nothing but 4 times 4 factorial. And I have 2 cases. In one case, the answer is 5 factorial. In the other case, the answer is 4 times 4 factorial. So my final answer will be 5 factorial plus 4 times 4 factorial. But I really want you to question why I use this plus here. Right? Why is there a plus? Why not a multiplication operator here? And really, if you think about it, if I make numbers which have 0, and if I make numbers which do not have 0, then these two events are mutually exclusive. Exactly, these are disjoint events. And therefore, so fundamentally, I split my event into two disjoint events. And therefore, I use the addition operator to count their cardinality. And exactly. Oops. So I hope this part was clear. Now let's try to do a few more problems. Let's say I had to find the total number of possible phone numbers of 10 digits, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I need to find the total number of possible phone numbers of 10 digits. How will I do that? One way to do that is to not invoke any principles we used and just say that okay, every number from 0 to 9999999 times will correspond to one unique phone number, which is correct, and that will give us 99999 10 times plus 1, because the plus 1 is from the case where we did not include the case where all digits are 0, right? When we're talking about a phone number, we are saying that the first place can be 0, right? Unlike the previous case. So yeah, there's that. So my answer for this will be 10 will be actually 10 times 10 to the 10 actually. Why is that? I have 10 choices for the first blank, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 10 choices for the second blank, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because repetition is allowed in phone numbers, right? So I have 10 choices for the first blank. I have 10 choices for the second blank, 10 for the third blank, and so on, 10 times. So I'll multiply 10 by itself 10 times, and therefore I'll get my answer as 10 to the 10. Right? Can phone number start with 0? I'm assuming it can. If you do not want to allow that, you can just consider it a 9. Right? I'm assuming a phone number can start with 0, and of course, I'm not sure if 0000000 would be a valid phone number, but I'm just considering that valid. Or if you do not like that, you could just consider it a 10-digit PIN code, right? Maybe somebody's 10-digit PIN code was all numeric, right? Anyway, so another problem we can talk about is maybe I have, let's say, 5 letters. Okay, actually, if you require a break, we're just going to end the session in a few minutes. So if you could just bear with me for a little more, we're going to end it in a few minutes, right? Cool. Thank you so much. So now that we're here, I have 5 letters. And I have 4 boxes. And the question is, in how many ways can I put these 5 letters into these 4 boxes? So I have letter 1, letter 2, letter 3, letter 4, and letter 5. And I have box 1, box 2, box 3, and box 4. Now, one way to look at this is that you can say that letter 1 has 4 choices. Letter 2 has 4 choices. Because letter 1 can go to either box 1, box 2, box 3, or box 4. Letter 2 can either go to box 1, box 2, box 3, or box 4, and so on. So each of these 5 letters, has 4 choices each. Therefore, I have 4 times 4 times 4, and so on 5 times, right? And I get my answer as 4 to the 5. Of course, I'm assuming that every box can hold any number of letters. That boxes are large enough to hold any number of letters, and that's where I'm getting this answer. And I'm pretty sure that some people would think about the answer as 5 to the 4, right? So let's try to analyze that argument, right? One could say that the answer is 5 to the 4, and trust me, it's wrong, but I'll try to explain why. 5 to the if you say that, okay, fine, this box has 5 choices, and this box has 5 choices, and this box has 5 choices, and this box has 5 choices, so 5 choices times 4 equals 5 to the 4. Then I'm going to say that this box does not have 5 choices, and even if you said it does, then the event of filling this box and the event of filling this box is not really independent, because whether I put letter 1 and letter 2 or letter, and so if I put all 5 letters into box 1, then I cannot put anything in box 2. So the number of ways in which I can fill box 2 depends on the number of ways in which I can fill box 1 and what I fill in box 1, right? And therefore the answer is 4 to the 5 and not 5 to the 4, right? Each letter has an independent choice of going to any of the boxes, because whether letter 1 goes to box 1, box 2, box 3, or box 4 has no effect on where letter 2 can go, right? And these events are independent, and therefore we can multiply here. And this is why I was talking about independent and disjoint events in the beginning, because people often confuse these, and many books themselves have different definitions for addition and multiplication rule. So I just wanted to sort that out. Dependent object to the independent object. Yes, you're right. In fact, you can apply this to many similar types of problems. There are problems which will ask you in how many ways can you wear n rings in our fingers, right? Saying that all fingers are sufficiently long to hold any number of rings, and you get the same answer fundamentally. So I hope you all enjoyed today's session. That's it for today. We will have another session where we will discuss some more advanced topics. This was mostly just the basics, right? Right. Thank you so much. Please fill the feedback form if you can.
Wish everyone to fill the feedback form.
Thank you. All right. So I guess we can end it here. Thank you so much, everyone.
Thank you, Aryan. Thank you for taking the session.
Thank you very much. I'll just leave the